Welcome to part 2 of my series on hiding the screen borders on the C64. Before I continue, I'd like to announce that May 4th marked the 3rd anniversary of the launch of Vision Basic. Woohoo! I'd like to thank all of you who have followed me these past few years and for all the support. It's not easy doing all this, that's for sure. And this year marks the 50th anniversary of the 6502 processor, which helped to bring affordable computers and gaming consoles to the masses. Without it, we wouldn't have our beloved Commodore 64, which uses an improved version of the processor called the 6510, which debuted 7 years later in 1982. And honestly, I don't know if it's 6502 or 6502 or 6510 or 6510. My apologies. In my last video, I showed how easy it is to remove the top and bottom borders of the C64 text screen, especially using Vision Basic, which makes setting up interrupts a whole lot easier. But if you want to use this effect in a game, you do need to keep some things in mind. With the full vertical screen exposed, you don't have a consistently good place within a single screen refresh to move your sprites during. When the borders are left intact, many programmers simply move their sprites when the raster beam is drawing those top and bottom borders. But since we don't have those top and bottom borders when using this effect, we run the risk of having our sprites flicker or shear when we try to move them about the screen. See, when you move a sprite while the raster beam is drawing it, or just before the raster beam starts to draw it, the sprite itself might vanish for a brief moment, or it may appear distorted on a horizontal plane. We don't want that. Basic programmers typically have no choice but to watch their sprites flicker or shear from time to time. I've already shown how to pull off the effect of border removal in my previous video. In this video, I'm going to show you my solution to preventing the sprites from flickering and shearing. I thought it would only take me about a week to come up with a solution, but I ran into some issues along the way, and my math wasn't mathing right either. Also, my regular PC computer and laptop are around 10 years old and can't run Windows 11. So with Windows 10 support ending this year, I've been looking into upgrading stuff there. And we had a tornado do some damage a mere few blocks away from us, so we were without power for a couple days. And I've just been ridiculously busy in general, so despite thinking that I can get another video out in about a month, it's been about 2 months. Okay, so on the screen you'll see something that looks a bit bizarre. I've made some changes to the program from the previous video, and I've added colorful bars and some characters to help with testing my solution attempts. Instead of having the sprites go both up and down, I'm having them all go upward. You won't see this happen until I start pressing some keys. Moving the sprites upward helps to detect flickering. Each sprite moves at a different rate of speed as well. Some even incorporate half steps in their movement. I left the garbage pattern in the top and bottom border areas just so that you can see where the borders are supposed to be. Garbage, garbage. The thin blue line in the outer border area, down here, shows the interrupt that handles the border removal process. The yellow area beneath the blue line shows how long it takes for my sample program to find a suitable raster line for relocating all 8 sprites on. The gray line in the middle of the screen, right here, shows when the key scan routine gets called. We would like for the computer to keep scanning for key presses, but we have to make sure that this process doesn't interfere with the other stuff we're trying to accomplish. There is another horizontal line, a pink one that you can't see right now, that shows when the registers for all 8 sprites are being updated. The solution I'm presenting in this video allows for vertical sprite movements for up to 4 pixels per screen refresh. Anything greater than 4 pixels will likely cause your sprites to flicker. So my approach to the problem is to find a large enough gap between all 8 sprites so that the sprites can be moved without causing shear and flickering. As a general rule, we need a clearing of about 4 raster lines above and below each sprite shape so that it can be moved without issue. So we can't move the sprites while they're being drawn, and we can't move them while the raster line is either 4 lines above or 4 lines below a sprite. This self-imposed limitation allows us to move them up to 4 raster lines up or down, hopefully without flickering. The problem is that we need to find this spot quickly because the raster line is constantly moving, and all the math involved does take up a lot of cycles. And we can miss our opportunity if we don't find a good spot quick enough. Okay, so the border removal process starts at raster line 249, down here. And I chose to start the hunt for a large enough gap when the raster has passed line 252. An NTSC machine only has 262 raster lines according to the book Mapping the Commodore 64. So that would imply that the raster lines run from 0 to 261. An online source that I found says that there are 263 lines instead, so I don't know exactly how many. Comment, let me know. PAL systems have more lines, but we need things to be compatible with both systems. So our hunt for a big enough gap needs to take less than 9 raster lines if possible, as far as how much time we have. And where do we hunt for this raster gap? Well, raster lines 249 to 262 are going to be busy, so that leaves us with raster lines 0 to 248. We're going to need a few of those lines to perform the relocation process, so I chose to limit things to a range from 0 to 240. Each sprite takes up 21 raster lines maximum, unless you double the height, and we need a clearance of 4 raster lines above each sprite and 4 raster lines below each sprite, so that means that each sprite kind of takes up 29 raster lines each. If you take the value of 29 and multiply it by 8 sprites, you get 232 forbidden raster lines. This leaves us only 16 raster lines left. This is our worst case scenario because you typically don't see all of your sprites so perfectly spaced apart. If sprites are overlapping in their respective 29 raster line territories, this opens up larger gaps for us. So the worst case scenario leaves us small gaps of only 2 raster lines each. And really, we need to try to relocate all 8 sprites during the first line of that 2-line gap. We only need to choose one of those gaps per screen refresh. If you're utterly confused at this point, it's okay, because you can simply use my routine and not have to worry about how it all works. Even I'm just hoping that I understand all of this to the level that I think I do. So let's see this in action for a little bit, and then I'll list the program so that you can see what's going on in the code. The sprites don't move unless I press a key, so let's press one now. Now you should be able to see the pink line at the bottom. And this is the raster line or set of lines that have been chosen for relocating all of the sprites. What I have found bizarre is that this is actually raster line 0. I always assumed that the first 50 raster lines were at the top of the screen, but when you look at the top of the screen, you can clearly see that a sprite that is 21 pixels tall is taking up most of the border space vertically. I tested this on real hardware, and the pink line is always at the bottom of the screen for raster line 0. Go figure. You can tell that it's raster line 0 because of the character at the very top left of the screen, an @ symbol. I'm poking these characters here to show us certain values that are in play. Anyhow, what we want to see in this demonstration is that the pink line must not touch any of the sprites as they are moving. But then I learned another peculiar behavior of the C64. Watch what happens when the cyan sprite approaches the pink line. And this is the cyan one here. So, I'm going to press the key about 16 times. 8, 9, 10, 11, 12, 13, 14, 15, 16. For whatever reason, the sprites will often touch the pink line at raster line 0, and I'm not sure why. This even happens on real C64 hardware. Let me further explain the characters at the top of the screen. Again, the upper left character, right here, is the raster line value where the interrupt happens, the interrupt that moves all of the sprites. The character below that is actually the raster line value that the actual code executes on, and this is usually only off by a value of 1. So there's a small delay between when the interrupt starts and when the sprites happen to see actual movement. The @ symbol is a value of 0 and the letter A is a value of 1. And we're talking about poke codes and not ASCII codes here. The letter T that you see here is the value for the vertical position of the first sprite, the red one. And the letter F here is the value for the vertical position of the second sprite, the cyan one. I could have added pokes for the rest of the sprites, but I didn't need to. It's just more code that I would have to have typed up. So, do you notice anything strange about these poke characters? Well, the F character has a poke code of 6, and this represents the Y position of the cyan sprite, which lines up with the pink line, which is at raster line 0 or 1. So this is where I start scratching my head. If both line up, how is one of them at raster line 6 and the other at raster line 0 or 1? Something's not right here. This even happens on real hardware. Now the cyan sprite did leap by several pixels with our last key press, so I'm sure that this explains part of it. If anyone can explain why this happens, I'm all ears. The one consolation here is that the sprites don't appear to flicker despite this strange behavior. If we press a key once more, like so, we see that the yellow area down here has expanded significantly, so this means that it has taken longer to find a suitable raster line for relocating all of the sprites on. And if we press a key 8 more times, 1, 2, 3, 4, 5, 6, 7, 8, you might have noticed that the gray line has jumped up near the top of the screen, right up here. It was down here. Again, this is where the key scan routine starts to do its thing. The pink line jumped all the way down to the bottom half of the screen. I have things set up to where the key scan routine will be executed at raster line 150 when the pink line is at a raster line of less than 128. And I have it set up where the key scan routine will be executed at line 50 when the pink line is greater than or equal to 128. The order for these lines will sometimes flip back and forth. I chose lines 50 and 150 because they seem like decent places for a key scan. You don't want the key scan to occur too close to the bottom or it will mess with the border removal process. So the general idea is to have one interrupt happen in the upper half of the screen and the other interrupt to happen in the bottom half of the screen. You also don't want the interrupts for the key scan routine and the sprite relocation to overlap either, so this provides adequate spacing. This does make setting up the interrupts a bit more complicated though. We could make the key scan routine happen immediately after we relocate the sprites, but I'm concerned that this might cause an overlap with the border removal interrupt when the pink line ends up close to that bottom border. And just to explain further, if we have this pink line down closer down to here, relocating the sprites, and then we put the key scan routine right after it, then we run the risk of overlapping the actual border removal interrupt. It's not like you're going to be able to interrupt the interrupt. Now, this method of trying to prevent flicker and shearing does come at a cost. Because the pink line hops around, there are times when some of the sprites may not end up being relocated during a single screen refresh, and there are times when they might be relocated twice. And I mean this from a visible standpoint. The sprites will get relocated with every screen refresh, of course, but the raster line might pass some of them by before they are relocated. Or they might be moved twice before the raster line reaches them again. It's a small price to pay, but you might notice it. I consider flickering the worst of the two evils. Perhaps someone more knowledgeable could code something better. I'm just happy that I've been able to remove the top and bottom borders, and I figured out a way to stop the flickering. Before I show you the code, which I don't plan to explain to extreme detail, I'd like to set this to full motion. Press return. And I'm going to get rid of this line. And it's not, oops, sorry, it's not equal 13. All right. And let's run it. You'll notice the pink line hopping all over the place now. Okay, so I'm not sure how many changes I made to the first several lines here from the previous video's version, but lines 10 to 170 pretty much set things up. The Y values in lines 120 to 150 are all doubled so that we can get some extra precision for the half steps. It's important to note that you can't actually move a sprite by half steps. For example, you'll notice the step values in lines 160 to 170 right here. These get added to the Y values, but the Y values get halved in the main routine. So when you see that A3 here in line 160 equals 7, the sprite will actually alternate between moving 3 and 4 pixels each time. Follow the math and you'll figure it out. And here is the main routine that handles the sprite coordinates. Line 500 starts the interrupt process. Then we have a bunch of math. We get a key press in line 800. If no key is pressed, we keep looping back. If return is pressed, we exit the program in line 810 and return things to normal. This is all pretty simple stuff. And again, a lot of things were explained in my last video, so I'm going to skip some stuff here. Though there are changes to this part of the code for sure. One thing to note is line 510 here. Here we are waiting for variable FL to contain a non-zero value. The first two instructions here are assembly language instructions, but this is pretty much what they do. They just wait for a non-zero value in the variable FL. See, the interrupt routine will set the flag variable FL to a non-zero value to indicate when it's safe to change the sprite position variables. And these here are sprite position variables, the Y coordinates anyways. And there are X coordinates elsewhere in the program. We want to make sure that these positions get put into the sprite position registers at least a single time. Depending on the speed of your program, they could end up being copied multiple times for a slow program, or not even copied at all if your routine is too fast. It's this latter case we're most worried about. Let me show you what I mean. Go up here. And run it. Yeah, that's not good. Way too fast. Okay, continue on. The routine here at line 1000 is a more simplified version of what you saw in the last video. Instead of using 2 interrupts to cause the border to vanish, I'm just using a single interrupt. I'm using the catch command in line 1030 to make this happen. Right here. After all, we're only having to wait a few raster lines before setting the border back to 25 rows. Okay, this mess here took me more days to program than I care to mention, and I'm not going to explain it to depth. If you know assembly language, you should be able to figure it out. Essentially, it tries to find a good raster line for sprite relocation. In line 1100, we start things at 0, but then we skip past several lines because the routine is a bit out of order. This has been done on purpose for the sake of eliminating some instructions. In line 1160, here, we're setting the X index to point at the 8th sprite's Y position. This value of 14 here indexes to the last sprite's Y coordinate when you add it to this address here. I suppose I could have used the Y index register instead of the X index register since we're dealing with only the Y coordinate of each sprite. Oh well, just a tiny bit confusing. In line 1170, right here, we're comparing the sprite's Y coordinate to the chosen raster line to see if the raster line is too close to the sprite. If the raster line is too close to the sprite, we'll jump to lines 1110 or 1120, here and here, to advance the raster line by a value of 23. I chose this prime number to kind of leap around the range of 0 to 140. But in the end, it's possible for all 141 lines to be compared against the sprites, because 23 does not evenly divide into 141. If the raster line is too close to any of the 8 sprites, we don't need to do any comparisons for the remaining sprites, so we just move on to the next raster line. Anyhow, we need to compare all 8 sprites against the raster line, so line 1200 here decrements the X index register twice so that we can move to the next sprite. In the first round, it will shift the focus from the 8th sprite to the 7th sprite. If all of what I'm saying is melting your brain, it's okay. I've done the complicated work for you, and you could just use my routines here. Now, line 1190 here says less than 5 in the comments, but it should actually say less than 6. I changed the value to 6 because the yellow and brown sprites were flickering a tiny bit. If this value is increased more than this, a suitable raster line might not be found. This will cause the branch in line 1150 to happen, right here. And line 1500 is a tiny detour that increments the screen color as an indicator that a suitable raster line has not been found. So in other words, if a suitable raster line has not been found, then this background color here is going to change colors. Those who are familiar with assembly language might notice that I've tried to reduce the computer cycles used in this routine through the elimination of unnecessary SEC and CLC instructions. And for example, this is a CLC instruction. If the carry flag is already set, you technically don't need to set it. And if it's already cleared, you don't need to clear it. But now we're wandering into the area of what might be considered sloppy programming. But when you gotta save cycles, you gotta save cycles. Notice how the BCC instruction in line 1190 here branches to line 1120 instead of 1110, for example. See, we could be branching all the way up here to 1110 where the CLC instruction is, but because it branches when the carry has been cleared, we don't need to clear it again, so it jumps to here. It's good to make notes that you're doing stuff like this, though, like the comment in line 1140, right here, SEC not needed. And the reason why the SEC is not needed is because if this branch is going to happen, then the carry is cleared. But if the branch does not happen, it'll fall through. It's going to be set, and we don't need to set it again. Anyhow, this chunk of code tries to locate a suitable line for sprite relocation. You can modify this code for your own programs in the following ways. For example, if you only need to use 7 sprites instead of 8, you can reduce the value of 14 in line 1160 down to 12. So just change this value to 12 if you're going to do 7 sprites instead. And you could keep reducing it by 2 for each sprite you want to eliminate. By reducing the number of sprites you use in a game, this helps to open up larger areas for sprite relocation, making the search easier for the program. And what if your sprites aren't 21 pixels tall, but actually shorter? You can increase the value in line 1180 by 1 for each pixel, right here. So if your sprite shapes are only 20 pixels tall, you can change the value of 232 to 233. Again, right here. And if your sprite shapes are only 10 pixels tall, then you could change that value to 243. You can't exceed a value of 255, though. Reducing the height of your shapes will also help to open up larger areas that can be used for sprite relocation. So I recommend not going with the full height of 21 pixels for your sprite shapes so that the interrupt can find a suitable raster line for sprite relocation more quickly. And I recommend using fewer than 8 sprites where possible. Again, all of this is just to prevent the interrupt from taking too long to find a suitable raster line for sprite relocation. And I recommend keeping your sprites from moving more than 3 pixels at a time. Vertically, that is. I mean, you could do 4, but, the fewer the better. And if you do vertical sprite expansion, you can decrease the value of 232 in line 1180 appropriately, but you'll probably also need to limit the number of sprites you're using. So if you double them to 42 pixels tall, you'll be better off only using 4 sprites instead of 8. And the value of 232 in line 1180 will become 211. The rest of the code will take too long to fully explain in this video. I have a variable RL in line 1410, right here. This is the raster line value that we need to set up one of our interrupts for. The variable CN in line 1430, here, is set to a value of 2 so that we can count how many interrupts we need to perform, besides the initial interrupt that removes the top and bottom borders. We need 1 interrupt for sprite relocation and 1 interrupt for the key scan routine. This is in addition to the interrupt that opens up the borders. So we have 3 interrupts total. The variable DS in lines 1450 and 1460, here, establishes whether or not the sprites will be relocated on a particular interrupt. A value of 1 means that they will be relocated. I completely forgot what DS stands for though. Perhaps it means display sprite, but that isn't exactly a good name. Maybe I should have changed it to RS. I'm sorry folks, I just wanted to get this thing out the door, so, these are changes I can make, but, it works. And if you're an adventurous sort, you can look at the rest of this code and try to decipher it. Lines 2025 to 2028 can be removed because they're the lines putting the strange characters on the screen. But by removing line 2025, you're also removing the decrement instruction for the screen color, so you'll also need to remove the increase instruction in line 2030, down here. I have a better version of this program I'll be showing you near the end of this video that removes all the crazy stuff that you don't want to appear in your own programs, so I suggest using that version instead. And this is pretty much the rest of the program. It's important to note that the gray line that is displayed by lines 2260 to 2264 is done before the key scan routine is called. You can't come back from the key scan routine, so I just wanted to display a few gray raster lines as a visual clue. These lines can be removed. Again, I have another version I'll show you that has all of the extra visual clutter removed. Now, instead of using the flag variable FL that I mentioned earlier, you could actually catch a raster line close to the bottom screen border. And we're going to type the following: 510, 242, 512. We're replacing that line and we're going to add one. So 53266, BCS 512. Okay. This should work as long as your code is fast enough. You should try to change the sprite position variables immediately after these lines using fast math commands, and then the rest of your main game loop can follow. This might be a better option than using the FL flag variable as long as your main game loop doesn't exceed a full screen refresh worth of cycles, including all cycles taken up by the interrupts. The reason I'm suggesting this approach is because you might be waiting for uneven intervals if you use the flag variable, so the game flow might not seem smooth. If you're a beginner and your code is a bit laggy, then using the flag variable will probably suffice. Now, we'll demonstrate that this actually works. Tap run. But you probably won't notice much difference. Okay, so now I want to show you a slightly different version I've whipped up. The main difference with this version is that our raster line selection process advances by 7 lines instead of 23. Notice this in line 1120, right here, 7. I tried running things from 0 to 240 by a step of 1, but this code just isn't fast enough at finding a suitable raster line that way. Occasionally, the process just takes too long. I've also tried a step value of 2, but that didn't work either. A step value of 3 did seem to work, but didn't work well for the screensaver you saw at the beginning of this video. So a value of 7 seems to do the job. Anyhow, let's run it. Okay, now I gotta press the key 23 times. Just watch what happens. One, 22, 23. Boom. I felt that this version reduced the flicker better than the other one, the previous version you saw, but notice the yellow area here, down here. It takes longer to find a suitable raster line, but it still does the job. So I guess use whichever version seems to keep the flicker at bay best. I'll show you what happens when you set the line search to increment by a value of 1. And we'll list 20. And we're just going to advance by 1. And then we'll do a 23 key presses. See, we lost the border effect here, and that's not good. That's why it just keeps flickering here. Despite how fast assembly language can be, it's pretty easy to eat up those thousands of cycles per screen refresh. And let's load up the final version that gets rid of the clutter. I don't need a disk. Okay, run. This is the most recent version of the program I loaded before this one, but with all of the screen clutter removed. There's no flickering, and as a trade-off, the sprites might stick a tiny bit here and there, as I mentioned earlier. I mean, like, I've noticed the brown ones stick a little time or two, so. So if you want to make a game where the top and bottom borders are removed, and you want to get rid of any sprite flickering, perhaps my solution will work for you. I enjoyed the challenge for the most part. I guess the part I didn't like was how long it took to figure it all out. Anyhow, until next time, time's up for this video. As usual, I thank you all for watching. Please like and share my video, and definitely subscribe for more similar content. And make sure to visit visionbasic.net.